So our last example of this section, we're going to look at the Space Shuttle solid rocket booster cases with the proposal that they were made out of carbon epoxy. So to replace the steel, save some weight, here's what the design criteria were. The diameter of these cases was 12 feet. The construction was to be filament wound, so you always have equal balanced plus and minus theta layers, low angle usually, of the helicals to take the axial loading, and 90-degree or hoop layers to take the hoop stresses. The operating pressure internal was about 1,000 psi. Each one of the motors generated a thrust of 3 million pounds. We'll see how that plays into our design requirements in just a minute. And we used a maximum stress criterion. So the maximum stress in the fiber direction, that is sigma 1, was limited to 200,000 psi. So that was the strength downgraded by a factor of safety of 1.4. So aerospace products tend to have a much lower factor of safety than most industrial products because you can do a lot of testing and verification. So over the 125-foot length between the connection points, the steel cases grew about 0.6 of an inch, and that was to be matched with the carbon epoxy case so that it didn't have to totally redesign the connection methods. And there was a minimum value of stiffness, stiffness being the modulus in the axial direction times thickness. 10 million pounds per inch was the requirement for that. That's like a spring stiffness, and so the idea was that you wanted the response of the case to be similar to that of the steel case, such that again the impact on the total system was really negligible. So we've got a little video we can go to here. And have to go back to this one. Yeah. So notice here about 3 or 4 seconds in that the shuttle main engines have fired. See the whole thing tip forward and then come back, and then when it's straight up and down again, that's when the shuttle boosters, solid rocket boosters, would fire. You can look at that again. So again, the shuttle main engines are going to fire first right here, causing the whole thing to tip because of the asymmetry here. And now once it's straight back up and down again, that's when the solid boosters will fire. Okay. So what we're trying to do, of course, is to minimize the weight, therefore find the minimum laminate thickness. All right, so as we said, the diameter was 12 feet, so radius of 6 feet or 72 inches. And we earlier found out how to find the stress resultants of a cylindrical pressure vessel, PR in the hoop direction, and PR over 2 in the axial direction. Now those would be if the case was closed on both ends, but of course it's open on partially on one end where the nozzle is, and so the imbalance gives you a thrust, which ends up putting the case wall axially, adds a compression load to the case wall. And so if we take that compressive load of 3 million pounds and divide it by the circumference of the case wall, pi times the diameter, ends up being 6,600 pounds per inch compressive. That gets added to the tensile load due to pressure, and so we come up with a total axial stress resultant of 29,000 and some pounds per inch. Now we also look at the axial growth requirement and just say, well, if we take the total length between the two connection points and look at the allowable change in length, that gives us a strain of 0.0004 or 0.04% strain. And so how are we going to approach this? Well, starting point, you would think that both the axial stiffness and the axial growth would be sort of the similar requirements. That is, if I can get high stiffness in the axial direction, that ought to be the best design. Now, winding is hard to do, get angles less than about 10 degrees. So let's try that. Let's try theta being 10 degrees. And so what we're going to do in Solver is we're going to try to minimize the total thickness. We're going to change two thicknesses, that is the plus theta and the 90-degree layers, making sure that the fiber stress or fiber direction stress is less than 200, less than or equal to, should say or equal to 200,000 psi in all the layers. The total axial strain less than 0.0004, and our stiffness value greater than or equal to 10 million pounds per inch. Now, one thing we'll put in the spreadsheet is that, again, it has to be a balanced laminate, so the thickness of the minus theta layer has to equal the thickness of the plus theta layer. In other words, our 10 and minus 10 here. And let's set that up in Solver. Okay, so I've just arbitrarily put in a ½ inch across here. I want to make sure that this thickness is equal to that one, because these are going to be the two that we're going to change, the plus 10 and the 90s. Here's our loading shown here, n sub x and n sub y. Now what I've done is made a couple of cells over here. This is the axial modulus times the thickness. That's the number that has to be greater than or equal to 10 million. So you can see this design's way over that. But this axial strain, I've just copied this from where we've calculated the strain down here. That has to be less than 0.0004. So the design that I've got here is not going to work. And let's set this up in Solver. So remember, this is what I'm going to minimize. I'm going to minimize this total thickness. I'm going to change the thickness of the plus 10s and the thickness of the 90s. And I have some constraints. Sigma 1 for all three layers, and again, ignore layer 4, it's got a 0 thickness on it here. This has to be less than 200,000 psi. Another constraint is that this axial stiffness value has to be greater than or equal to 10 million. And finally, one more, this axial strain has to be less than or equal to 0.0004. And click OK, and let's try to solve. And you see what we come up with is a thickness of over 2 inches. You can see that we just hit the strain here, but we're way over designed as far as the axial growth, excuse me, the axial stiffness goes. So the strain seems to be the driving factor here, the critical factor. Okay. So again, there's with theta being 10 degrees. And also we found that the stresses in the plus and minus 10 are relatively low. The 90s are at their limit of 200,000 psi. So again, axial growth appears to be critical. Now, what if we just try a higher helical angle? That doesn't seem logical necessarily, because again, you've got two things in the axial direction, stiffness and growth. But let's try it anyway. So we're going to switch to 30 degrees. And so I'm just going to change the 10 to 30. And again, we've got plus and minus 30 here. And all the constraints are the same, so we can just run it again. Oh, look what we come up with, a little over 1 inch thickness. So definitely a better design here. Let's go back and again summarize that design. Looking at the stresses, nothing significant there, but notice that the axial strain here is actually negative in this case. So with 30 degrees, the stiffness became critical, and not the axial growth. So before we look at trying to optimize and say, well, what's the best angle of that, let's take a look at the mechanical properties of both the plus minus 10 and plus minus 30 designs we've come up with. Here we go for the plus minus 10. Here we go for the plus and minus 30 degree. And the key is this value right here, the Poisson's ratio yx. So when you have the higher angles, you get a Poisson's ratio that's greater, and what that causes is that as the case stretches in the hoop direction, then it causes contraction in the axial direction, and it's much greater for the 30 degree than it is for the 10 degree. And we can look at the optimum angle here in just a moment, but first of all, let's just look and see if we just look at the axial stiffness and axial growth requirements separately instead of at the same time. You can see if we design for axial stiffness, obviously the lightest weight case we're going to have as close as we can get to a helical angle of 0, and as we increase the angle, of course the stiffness goes down, and so the required thickness goes way up. But when we look at the requirement for axial strain, just the opposite. So you can see at 10 degrees we had to be over 2 inches, but at 30 degrees it's a little bit actually, well, 30 degrees then the axial stiffness becomes critical, and so our design had to be up there. So the best design was where those two cross. At about 27 degrees, that's going to be the optimum angle. It's going to be a little over 1 inch. So back to the spreadsheet. And so really all we have to do now, and remember this cell is set to be the negative of that cell. So all we have to change in Solver is we're going to allow one more variable. We're going to let both the thickness of the plus theta, the thickness of the 90, and the angle theta itself to vary. And we come up with an optimum angle of about 26.6 degrees. And now you can see we're just slightly over 1 inch thickness. And so that was pretty much the design that was made. Here's the 4 segments of the filament wound case all together and ready for static testing. And as I mentioned in class, this design never flew because the first flight set was at Vandenberg Air Force Base when the Challenger disaster occurred, and so this project never went on. But again, it did show that it was a feasible design. All right, so next time we'll look at failure criteria.